Hello, my name is Samuel Flores, and I am the course coordinator for BK0001 Bioinformatics. Today we're going to be talking about machine learning. So we're following Michael Nielsen's online book. We're only going to do chapter 1 in this course. This barely scratches the surface, but nonetheless, it should show you a real example of how you can implement deep learning for a relatively simple machine vision problem, and maybe it'll give you a taste of something you could do more of, for example, in a thesis project or a project course. So the reading is chapter 1 from Nielsen's book, and yeah, and I know that I'm using his figures in my presentation. So we're going to talk about MNIST and a large handwriting sample data set, and how we can learn to recognize those digits, or any digits trained with this data set. We're going to talk about the Rosenblatt Perceptron, which basically set the foundations for neural networks. We're going to talk about how we can put perceptrons into networks, and then prove that perceptron networks can implement any logical function. Then we'll talk about another activation function, which is sigmoid. And we'll talk a little bit about sort of qualitatively how to train a neural network, and then we'll give a few teasers about how we move from a simple neural network like the one in that recognize the MNIST data set and move on to more complex networks that solve other machine vision problems. So MNIST data set was collected by having high school students and postal workers just write out a whole bunch of numbers. And so if you look at handwritten digits, so just the ones that are on this slide, you can start to appreciate why it's such a hard problem. Just how people can write 9s or 7s. Like, what's the difference between a 9 and a 7? Is a 9, you might say, oh, a 9 has a closed circle. But how many people don't write 9 like this, right? How many people don't write a 7 like that? So it can be quite difficult. So that there are certain elements that they might recognize. Like, you might say, oh, a 7 has a diagonal line going from the top right to bottom left. Well, yes and no. Some people write it like this. Some people do this thing. Some people write their 1s like 7, especially people from Germany. So the neural network can learn to recognize elements, but it works actually pretty well. But the point is that this was a problem which is not easy to solve by earlier methods. For example, heuristic methods. If you try to just have some formula that says, look for elements that look kind of like this, look for circles, look for slashes, look for vertical lines, those were surprisingly limited. Okay. So perceptrons. Perceptrons were published by Rosenblatt in 1958. And so he takes some number of inputs. It can be anywhere from two or more inputs. So you can imagine that these can be basically any number. And in here there is a sum. And then if this sum is above a certain threshold, then this output goes high. In other words, becomes 1. And if it's below that threshold, then it's 0. So it's basically, basically a step activation function, right? So this is your sum of all x's, shall we say, sum over I. So this step activation is not differentiable. That's going to turn out to be a problem that we'll come back to. But of course it was, we were just starting at this time. and we'll show that this perceptron is actually pretty powerful, even if we don't use it in this way anymore. So Rosenblatt's paper got a lot of attention, and I think it was mostly, firstly, it was a scientifically important paper, but secondly, because he did so much work to connect it to the human brain. Like his idea was that neural networks can solve problems, but the other motivation is that they can maybe teach us something about the human brain. And that's actually continues to this day. To this day, when you go to a neuroscience talk, very often they'll connect their work to deep learning. And when you go to deep learning talk, they'll connect their work to neuroscience. Let's see. So a single perceptron is quite limited. So if you're thinking about what it can do in terms of logic, like it can reproduce maybe an or maybe an and. Let's say. So an or has a truth table. It looks like if your x1 is 1 and or let's just start with zeros. If your x1 is 0 and your x2 is 0, then your output will be 0. If your x1 is 1, x2 is 0, your output will be 1. Similarly, if 0 and 1 will give you 1, and also 1 and 1 will give you 1. So that's OR. And so if you sort of plot x1 versus x2, then this will give you 1, right? And so you could imagine that, this will also give you 1 here, and this will give you 1. This will give you 0. So you can imagine there's I could draw a line here where everything on one side of the line is going to be a 1, and everything on the other side of the line is going to be a 0. And a perceptron can give us that, right? Like if we can adjust the weights such that the line has a slope and offset that we want, or the bias, the threshold we can also move. So because remember here where the output is going to be 1 if the sum of these two is above a certain threshold, and we're free to choose W in a way that produces the function we want, right? So we can do that, and we can also do AND, right? So if we have x1 and x2, and then AND would look like, let's say 0, 0, 1, 0, 0, 1, 1, 1, and would be like 1, 0, 0, 0. So in that case, you would want to put your line here. So everything sort of to the top right of that line would be 1, everything else would be 0. The problem is when you get to anything non-trivial, for example, XOR. So XOR looks like let's say you got 0, 0, 1, 0, 0, 1. You can think of it as OR, but only OR. In other words, either or, but not both. So that means that 1 and 0 fire 1, 0 and 1 will give you 1, and the others will give you 0. So even 1, 1 will give you 0. So that means that you want a function that that gives you 1 here and 1 here, but 0 here and 0 here. So I think it's pretty clear there's no line that you can draw where one side of the line should be 1 and the other side of the line should be 0. You need something a little bit more sophisticated than that, right? And so this gets into the issue of hidden layers. So no matter how many neurons you have in a single layer, like there's just no way to do this with an input layer and an output layer the way you would do it with just a Rosenblatt perceptron. Instead, you have to put several perceptrons, like at least one hidden layer, right? It's actually possible to use a perceptron to reproduce any logical function, no matter how sophisticated. And I'm not going to prove this now. Maybe you can just look it up on the internet if you're curious. But I'll just postulate that, or assert that that engineers can prove using Morgan's laws and so on that they can create any gate using only one type of gate called the NAND. So NAND means it gives you a 1 for anything that's not 1 and 1. In other words, it's a negation of the AND. Remember I said AND was like this? So basically a NAND would be the negation of that. NAND would be 1, 0, 0, 0, right? Oh, I'm sorry, no. It would be 1, 1, 1, 0. It's not the negation of OR, it's the negation of AND. Sorry about that. So not AND. NAND, so 1, 1, 1, 0. That's NAND. Anyway, so you can create any gate from NANDs, and a perceptron can create a NAND, right? Because I already showed you that it's or I argued that it could generate an AND. So a NAND is just the negation of that. So it just means that everything on the lower side of this line would now be a 1, and the top right would be 0. For instance, here's the bitwise sum. Let's just say we have a simple problem that these two are binary inputs. These can be 0 or 1, and you want the sum and the carry. So so if you have only 1 bit in the input, then the output should have 2 bits, right? So for example, if we have 1 plus 1 in binary, that should give us 1, 0, right? That should give us 2. So let's just we can just kind of verify that this is true. So let's say this is 1, this is 1. You put this into a NAND, that would give you a 0 on the output, because again, AND would give you 1, but this is not AND, so it gives you 0. And then 1 and 0 would give you a 1, and that would be the same thing here. So here we have 1 and 1, that's not AND, so that should give you a 0, right? So your sum is 0, that's this thing, but then you have the carry bit to worry about, and so you take the only thing that the NAND for the carry bit sees is 0, so 0 and 0, that gives you a 1, right? So that gives you this 1, so that works. So we showed that we can do this 1-bit summation using NANDs. And so that means that we should be able to do it also using Perceptron, right? Okay, so the same thing can be implemented with perceptrons. Like each of these NANDs can be turned into a perceptron if you find suitable weights. And there's a range of W1s and W2s that will give you the right results. W1, W2, and bias. Right, and so therefore we can create any function, right? All right, and I would like you to note that the sum is going to be the same as XOR. Remember that we wanted to solve the XOR problem. That meant that, oops, sorry about that. That meant that if x1 is 0 and x2 is 0, then XOR should be 0. And if it's 0 and 1, then that should be 1. 1 and 0 should give you 1. And 0, 0 should be 1. And you should be able to verify that sum does this, right? Because if you add up binary numbers, so this is XOR, and the sum should give you, if you have 0 and 0, you get 0. If you got 0 and 1, you add 1, get 1. Add 0 and 1, 1 and 0, and you get 1. Oh, sorry, I meant to say 1 and 1. If you add 1 and 1, you also get 0, right? Because 1 plus 1 is 2, but we're in binary, right? So there's 0 in the units place. There's a 1 in the 2's place, right? So the real sum, 1 plus 1, is like that in binary. But anyway, the sum looks like exactly like XOR. So I would argue that, or I would assert even that we've solved the XOR problem as soon as we've solved the sum. We can go into this in more detail in the discussion. Yes, there's a bit of a problem with the perceptron in that Rosenblatt went with a step function, right? And it's not differentiable. One of the the definition of differentiability includes this idea that that you have to be able to that you'd get the same slope whichever side you come from, and it should be a continuous slope, and so you just don't have that with a step function, because your slope is basically, your derivative would look like 0, 0, 0, except infinity, and then back to 0, 0, 0. So that's just not a continuous derivative. And the reason we want to be able to have a continuous derivative is because it turns out that if we know the right answer, like we know the output we expect, which is the case when we have a training set, which we're always going to need to train a neural network, then we can look at the difference between the output we got and the output we need, and then figure out how to change these weights to get that output, right? That's the whole process of training. And so we do that by a process called backpropagation. And we're not really going to get into that in this course, but you just need to know that the activation function needs to be differentiable in order for backpropagation to work. Okay, so we can use any differentiable function, and actually there is no one answer as to what activation function is best. There are some that are more popular than others, but they all have different advantages and disadvantages. So the one that you might want to consider is sigmoid activation. And sigmoid activation basically just means that your activation looks like a sigmoid. So that looks kind of like that. And that has a nice property that it's differentiable. There are things that are easier to differentiate. Like, for example, the easiest thing to differentiate is just a straight line. And there's something else that's not a straight line, but it's piecewise linear. So it's called ReLU, rectified linear, and that means that above a certain threshold, it's a linear line with non-zero slope, and below that threshold, it's a line with zero slope, or just zero. Let's see. Yeah, and so the sigmoid for multiple inputs is just defined like this, where the input is just instead of being one number, it's basically the sum of all the inputs. Okay. Minus the bias. You always have to have the bias. Actually, the bias. I mean, in the textbooks, it's like this, where the bias is considered to be some different number, but lots of people will represent it like this, where XB is actually considered like an input, but it's always equal to 1, and then the bias is the weight that gets applied to that input. It's a technicality, but it makes the math a little bit easier. Okay, so that's a sigmoid activation. Yeah, looks like this. Yeah, and so now, like I say, now you're going to be able to relate. If you're able to differentiate your function, then you can relate the output, the change in output, to the change in your inputs, or a change in your weights, right? And like I say, that's the basis for backpropagation. So if you have at least one hidden layer, you're already in the threshold of deep learning by sort of the classical definition. And as I pointed out, like, to do anything non-trivial, you're going to need hidden layers. And it's kind of an art to designing a neural network. Nobody really knows how many hidden layers you'll need, or the size of the hidden layers ab initio. Like there's always a bit of trial and error. And if you have more experience, then you're going to get better at it. But there's nobody that just says immediately, oh, this is the exact number of hidden layers I want, or this is the exact size of the hidden layers. You always have to try a bit. And yeah, and there's advantages and disadvantages. You might say, oh, if more parameters means that I can learn to solve more complex problems, then yeah, I'll make it hundreds of layers deep, and each layer will be thousands of nodes. It doesn't exactly work like that. There's also downsides to big networks. The bigger your network is, the more training time you have, and also the more susceptible it is to overtraining. So overtraining basically means that you have more parameters than you have data, and that's actually neural networks can actually be surprisingly tolerant of this problem of less data than fewer data than parameters, but nonetheless, it's something you have to be careful about. Let's see. Here we're only going to be talking about feed forward. So when you see like all the arrows pointing from left to right, so you see these guys. Here's your input. Here's your hidden. Here's your output. The information flows from the input to the middle to the output, right? That's it. That's a feed forward network. There are recurrent neural networks, so maybe one layer could send information back to a preceding layer, and that gets a bit more complicated, and we're not going to get into that. So the example that we're going to be doing in the lab is classifying handwritten digits. So your first problem when you're trying to read digits is just identifying where the digit is, right? And so that basically means like let's draw a bounding box around each digit. And Nielsen calls this segmentation. I don't want to be a semantics Nazi, but everybody else would call this basically object detection. Segmentation is a different task. It just basically means assigning each bit a certain label. Like for example, it might be that you say, oh, assign like all the ink that's on the paper as ink and everything else is background, right? So then it would, like, if that's your task, segmentation would cut out this thing, right? And tell you, oh, that part is digit, the rest is background, right? Anyway, so object detection, as I would prefer to call it, would be drawing bounding boxes around each of these digits, right? That's a separate task, like I say, and it's not one that we're going to treat in this course. And in the MNIST data set, this object detection has already been done for you, and all you get is a box. In fact, every digit is a box 32 by 32 pixels. And your task is to then classify. So classification is when you take an object and put it into a certain category, right? So in this case, your categories will be 0 through 9, right? So this would obviously go into category 5, and this will go into 0, and so on. So remember, detection is separating out the objects. Classifying is telling you, putting a label on the object, specific label. Okay, so the first thing you could try at classification is a 3-layer neural network, meaning one hidden layer, the output layer, and the input layer. Your input layer oh, I'm sorry, I misspoke just a bit earlier. It's not 32 by 32 pixels, it's 28 by 28. But anyway, so 28 by 28 pixels is this input layer. And it's, most of the time when you see these diagrams, you don't try counting the actual neurons, because very often there's more neurons than you can really draw on the paper, right? In this case, 784 neurons. And so you'll also notice they represent this as a line as opposed to a 2D input. You can actually do it either way. Like there's something called flattening, where you take your like all your 784 pixels, and instead of representing like this on a grid, you spread them out. So like you take the first row and then you put the second row after that, and so it becomes 1D. And there's absolutely nothing wrong with that. Like the neural network can handle it absolutely fine. It does not care about that. So the fact that it's in a straight line, that's actually okay. But the number of neurons is what's not right. Then you have a hidden layer, and you can play with different number of neurons. One exercise will actually be to try one neuron and see if it gives you any classification accuracy. But at any rate, this is the main thing you're going to want to play with, and you can even add additional layers and see how it goes for you. And then your output layer is the one that actually classifies your image into 0 through 9, right? And so one neuron fires when it thinks it's a 0, then the other neuron fires if it thinks it's a 1, and so on. So this is a bit something that for a beginner might be a little bit counterintuitive, because you say, okay, 0 through 9, 10 digits. Like I could represent that with what 2, 4, 8. With 4 bits, I could represent that. So I would only need 4 neurons in the output. Turns out that's not a good idea. Even though it might look more efficient, the one hot has a virtue that it separates your variables much better, right? So like for example, this neuron that's wants to detect a 0, it looks at all of these neurons before it, which are encoding some information that's relevant to different digits. Like for example, curve at the top right of like a semicircular curve at the top right, a semicircular curve at the bottom left, semicircle at the bottom right, semicircle at the top left, that sort of thing. It might be able to get from the hidden layer, and it looks at them, and if it ticks all boxes for what it expects to see in a 0, then it fires, right? And these weights are all adjusted to only to affect the detection of zeros, right? You don't have to worry about like, detection of 1 wants this weight to be this thing, and detection of 0 wants this weight to be the other thing. So it turns out like this actually saves you a layer. If you wanted to do it represent this with let's say with 4 neurons and then decode it later, that would actually take more layers, one more layer, let's say, probably. So yeah, so let's see. So that's one hot encoding. Yeah, that's all I want to see on this slide. All right. So yeah, so I was telling you that the hidden layer should start to learn some things that it thinks are relevant. Like it learns to recognize certain elements that will be informative about which digit it is looking at, right? Like I mentioned a 0. It might want to break it up into these 4 elements, and if it has all 4 of them, more or less, then it'll tend to fire as a 0. Whereas if it just has one of them, and then it has something else that tells it it's actually a 7 or a 5 or something, then it will fire those other output neurons. So yeah, I mean, and you could do an exercise where you try to do this with not the one hot encoding, but rather like binary encoding. Okay, so I told you that there's going to be something called backpropagation, and in this course, as I said, we're really not going to get into it. but I just want you to get a qualitative understanding of gradient descent. Gradient descent just means that we have some function which could be a complex function. In our case, it'll have many variables, not just 2 as shown here. And we're not at some optimum. We want to be down here at the optimum. Basically, whatever maximizes our accuracy or decreases our loss. We have these different ways of quantifying how inaccurate we are, right? So we want minimum inaccuracy, if you want to put it that way. And we can actually compute if our functions are differentiable. We can actually compute how much a change in one variable, let's say one of our weights W1, and how much effect that will have on our output, right? Then we can also compute what effect a change in W2 would have on our output, and that'll have some different function. And then you add these two up, and you say, okay, so there's a net gradient going in a certain direction, right? And so what you want to do is you want to follow the gradient, and then you might have to take several steps, but eventually you'll hit the bottom of this potential. And actually, you're not going to exactly use gradient descent. If it's a very large network, you might do something called stochastic gradient descent, but then that gets a little bit more advanced. Let's see. So Nielsen distributes the code for all this in his on his GitHub repo. His code only works in Python 2. So in the lab, we're probably going to use, I ported that to Python 3. It actually turns out that other people have also ported it. And in the lab, we'll use either mine or one of those others because it's going to just be so much easier to work with Python 3. Python 2.7 is completely dead. I mean, it's been deliberately killed. And a lot of this old code relies on Python 2.7. And in general, you just want to be with Python 3. So anyway, this first code snippet, all it's basically doing is kind of defining, sort of creating random initial values for your biases and for your weights based on some input vector you give it. So if you say 2, 3, 1, that means that I have 2 neurons on the input layer, then I have 3 neurons in the hidden layer, and then 1 neuron on the output, right? And then maybe it's going to assume that it's densely connected, meaning that all neurons on each layer are connected to all neurons on the next layer, something like that. And so this basically says, like, your weight here would be some number, right? And it'll just assign random weights and biases to everything because you have to have some sort of starting point, right? It's probably not a good idea to start with all zeros because that might end up biasing your results. It's better start to randomize. Okay. And then we have to implement the sigmoid. And so you've learned, I believe you already learned about NumPy, and this is a really nice library. The way you implement some mathematical function is basically hardly uses more characters than are needed to actually express minimally the mathematical function, like using math notation. So here, this is a sigmoid. Like you saw this formula earlier. I mean, it's got the sum in there implicit in the fact that the input is an array. So basically, all you need to know is that this thing takes some sort of array of inputs, x1, x2, x3, and so on, and then and weights, and biases, and then puts out one number. Because remember, the neuron takes in lots of inputs but fires only one output. Okay, and then and here's a feed forward function that takes in the inputs from one layer and produces the outputs that go into the next layer. Stochastic gradient descent. Well, this is a method that turns out gradient descent can be a bit expensive, given if you have a lot of variables in your network. And let's say if maybe your activation function is sigmoid, you end up doing a lot of derivatives. So stochastic gradient descent is a way of choosing subsets of those derivatives to compute. And and just ignoring others, and it turns out to be a bit faster, or a lot faster. The question is how accurate, how good it is at descending and finding the minimum. But in any case, it's a very popular minimization algorithm. I wouldn't say you need to really get too much into this, but anyway, the code is there in the book. And then there is a backpropagation step, and remember that's the algorithm that's gonna determine what the new weights and biases are based on the previous weights and biases, and how close it came to the test, like the test set gold standard result. Okay, and so in the lab today, you're going to do a simple exercise where you're going to use the GitHub. I mean, you can use my GitHub repo, and like I say, it's possible that we could use another a different port, but this one I know works, at least for this exercise. So let's see. You need this variable that tells Python where to find Nielsen's modules. For example, specifically MNIST loader. There's a file called MNIST Actually, I'm not going to put right there, but when you look for it in that directory, you're going to look for something that has this .py. You don't need the .py here in the import statement. But anyway, so the import statement loads that, and that basically just says go and get the zip file, unzip it, and that has everything, like the entire MNIST data set, and divide it into test and train set, right? Remember, we didn't say too much about that, but it's actually really important that you remember you have to have some data that's in your test set, or sorry, your training set that you train on, and then different data that you test on. Like if you have the same data in your test and train, then you could easily memorize your data set and get really high values or really high accuracy, but it's not true, because then when it goes to work on unseen data, then or new data, like some handwriting samples from new people, then it wouldn't perform. Like you would note a huge decrease in the accuracy on new data. So anyway, this does the work of separating into test and training. Oh, here, this step, you're doing that. And then you need this import, this network.py file, and it'll find that in the same directory. And then you instantiate network. Remember, this is 28 by 28, so that you can check that should be 784, the number of pixels in these handwriting sample images in each of them. And then they're saying, okay, let's try 30 neurons in the hidden layer, right? So remember, we had a hidden layer that had these 780 neurons in the input, and then now they're saying this hidden layer should have 30, right? And then the output layer should have 10. And that, of course, you don't have flexibility in that, because 10 is the, how many neurons you need to encode digits 0 through 9. So the only one you can really vary in, sort of non-trivially is the number of neurons in the hidden layer, and also potentially the number of hidden layers. Here's an additional step that I had to do to port from Python 2 to Python 3. It turns out if you do it in Python 3, like their pickle library puts it into a zip rather than a list, and you want a list, right? So anyway, you have to transform it to list. Same thing, so training and test data, and then you have to have validation data. So that's something that's left out of the whole test train cycle. Let's see, this is a stochastic gradient descent algorithm. So and it's giving you some sort of parameters for the gradient descent, 30 epochs. That's periods of minimization time, let's say. 10 mini batches. Mini batches are just ways to break up the data set and just do one bit at a time. And then you have a learning rate of 3.0. So learning rate is basically like if you're following, like if we go back to the gradient descent, like if you're following along the gradient, let's say here, you could go a little bit of the ways this way, or you could go a long way. And these have disadvantages. Like the long way is like fast learning, but it's also greedy. It has a big risk of overshooting the minimum and ending up in a local minimum somewhere else. On the other hand, a very small descent might get stuck in some tiny local minimum, not be able to get out of it. So there's a sweet spot, and it's kind of an art to find it, not so much a science, or less of a science, more of an art. You just have to play with it a little bit. So anyway, the learning rate is so that's the learning rate is 3, right? And if it looks like it's not performing well, it's not getting a nice accuracy, like well above, let's say 0.9, then you might want to play with that number as well. Yeah, then it should start putting out this code, or sorry, you're monitoring the convergence here. Like so it's saying that it correctly classified 9,129 digits out of a test set of 10,000, right? So that's already pretty good. Even the first epoch, it was already getting over 90%. But if you let it run a little bit longer, you'll get, who knows, 95% or something. And again, once you change the size of this hidden layer, then your performance might get better, might get worse. And again, one thing that you should try is just one neuron in the hidden layer and see what that gets you. It's not exactly just adding up the number of black, how much ink there is on the paper, although that's something that Nielsen alludes to also. It's a little bit more than that because it can adjust the weights, but it's very close to just simply adding up how much ink is on the paper. And there is a correlation between which digit it is and how much ink it is, right? 1 takes less ink than an 8, for instance. Okay, so that was a very simple-minded neural network, but you'd be surprised at how many useful problems you can solve with something as simple-minded as that. Just densely connected layers, maybe not even very deep. If your problem looks like anything like this, or even if it's different but doesn't seem to require greater sophistication, then certainly go with it. So let's talk a little bit, without actually getting our hands dirty with it, let's talk about how this can solve more sophisticated, or how this fits into like a maybe more sophisticated method that does more amazing things than this. So so the question is, let's say you want your task to identify humans, right? And you have these pictures. So if you're a computer and you don't know how to approach this problem, one thing that you might try is looking for eyeballs, right? So how's this related to handwriting recognition? Well, I mean, when you think about it, what's the difference between recognizing a digit and recognizing an eyeball, right? I mean, eyeball, what does it look like? Maybe something like that. So it's almost, well, maybe the way I've drawn it, it's a bit more sophisticated than a digit, but you see the point I'm getting at. I mean, you might be expecting to find some kind of curve that's concave downwards, another one is concave upwards, 2 concentric circles, something like that. I mean, there could be a wide variety of geometries that still look like eyeballs, right? And there's something called a convolutional neural network. So one thing that we didn't get into was that even if you're done training this network, if somebody were to write their digit very small, so that it only takes up like a tiny piece of the picture, then we might not recognize it correctly, right? Because our neural network is trained on digits that are all kind of normalized to be the same size. So, and that's actually not as trivial a problem to solve as you might think. But the point is that if you could solve the problem of like just saying inside of a given box of a certain fixed size, is that an eyeball or is that something else? It's very similar to this MNIST classification problem. So, so you can imagine that maybe we could solve that problem for some subset of this larger image, right? Maybe we could have like a very simple network that just says eyeball. Is that an eye? Is there an eyeball there, right? And then maybe shifts to the right a little bit and asks the same question, is there an eyeball there? And then shifts to the right a little bit, is there an eyeball there? Turns out there is such a method. It's called a convolutional neural network. And basically it just has a, a grid that could be the same size, the same dimensions as this. But it uses something called weight sharing, right? So it has this neuron doesn't look at all the neurons in the input layer, but only looks at neurons in that one square called a kernel, right? And then the neuron next to it might look at all pixels in that next kernel that's right next to it, and so on. And so because you're using this thing called weight sharing, all the weights that on the edges or connections that go to this node are exactly the same as all the weights that go to this node. And so this simplifies your training a bit. A lot, just because there's fewer actual independent variables that you have to solve for. And so you can get this thing to tell you, okay, maybe go through a couple of hidden layers, but one of those hidden layers might have something that tells you that just lights up with eyeballs, right? And so and that's looking at this preceding layer somehow or other. And so with the kangaroo, it might fire here, right? And in the case of this little boy, I guess it's a boy, it might fire here and here, right? In the case of this field of stars, I don't know, maybe it would fire for a few of these galaxies, who knows? But then you could have another hidden layer that kind of specialized in eyeballs, right? And the way you actually implemented this could be a number of different ways. Like I would do this as like each of these eyeball and nose and all these other layers, those could be channels within a single layer. It's kind of tomato type of thing, it's semantics in a sense. But anyway, I would work with channels. And anyway, so nose, like it could be trained, it could figure out how to recognize noses, right? A nose just minimally, it looks like that, or maybe it could look like a bit more like, this, or something like that. But anyway, the point is that just like we can recognize different, a single digit written by different people in different ways, we can recognize different types of noses. Anyway, so this might, for the little boy, this might fire somewhere in the middle, right? And then you can have ears, right? And this one, it should fire here for the little boy. And for the kangaroo, well, it just depends on how you trained it. If you never train it it might not recognize any ears at all, or it might recognize that it has ears, but that they're above his eyeballs, right? And so finally, later on, you have some kind of integration layer. Like this is mostly happening implicitly. Like you don't actually necessarily have control over how your neural network learns. Like what features it learns. Like that's kind of one of the cool things about it, is that it might catch features that you didn't even realize were important. That's also how it could be dangerous. I mean, you've seen how it can be developed, for example, racial biases and so on. But anyway, the point is that you can have some sort of layer here that looks like all these preceding layers, or maybe the preceding layer with the many channels, and it relates the different features that it detected and said, okay, now I know that humans have, one or two eyeballs. The nose is below the eyeballs. The ears are also a little bit below the eyeballs, maybe. Definitely not like way above their eyeballs. This sort of thing. And then it can say, it could actually just be a layer that just says human and non-human. Sorry about my handwriting. But anyway, that could be your output layer, just two neurons. Yeah. And there's really just so much more to talk about when it comes to machine learning. This, like I say, this just scratches the surface. But I wanted to give you a little bit of an idea of how something simple like handwriting recognition is similar to a little piece of a neural network that does something much more sophisticated than this. So things that could be implicitly being resolved in these hidden layers are, is there an eye on top left? Is there an eye on top right? Is there a nose in the middle? Is there a mouth at the bottom? Is there hair on top? And then you get like, is this a face or is this a human face? That sort of question answered. Yeah. Right, and this is, the question of recognizing individual elements, like the different parts of the face, like that could also be kind of broken down if there's multiple layers into this sort of thing. Like, just like recognize zeros. Just recognize a zero. Remember, it could have been recognized by, curve here, curve here, curve here, and curve here. All those exist, and it's a zero. It's that sort of thing. Even something as simple as an eyeball, where it could have been broken down into things like concave downwards, concave upwards, concentric circle in the middle, that sort of thing. Okay, and then again, shout out to the bioinformatics section, and I will look forward to seeing you in the discussion and in the lab.